This video is going to be about the hows and whys of Ford's cabin. The design, why we built it the way we built it, how we put the pieces together. Let's start with the design. The design was entirely Ford's. I suggested a bunch of more alternative, shall we say, hippie designs for him. Little portable cabins, things that combined like a workspace with a living space above it, stuff like that. And he wasn't having any of it. He knew what he wanted, and eventually he got it down on paper clear enough so that I could design him figure out how to actually build it. So what he came up with, 20 by 24, kind of a story and a half, knee walls on the upstairs, and a structural ridge. And then I just figured out how to put that into an actual building. We were somewhat limited just by the sawmill. When I realized he wanted knee walls and a ridge, so we'd have to have a structural ridge to carry the rafter load, and the sawmill can only cut 18 feet, so that kind of limited our ridge height there to 18 feet. So then we went down on the sidewalls to 13 feet, which gave us a 512 roof pitch, which is fine in this climate. A little flat maybe, but fine, and certainly a nice roof to walk on and work on. And that gave him a knee wall upstairs of roughly 5 feet, which makes most of the upstairs pretty much completely usable. Actually, you can walk almost right to the eave in the upstairs. It's a very spacious feeling up there, and 10 feet tall at the peak. There was a pre-existing dilapidated, mold-filled double wide trailer on that site. The previous owners had bought a trailer and then done a pretty good job of turning it into a double wide. The part that wasn't the trailer, they'd had a sonotube foundation, just 8-inch sonotubes, about 2 feet in the ground. They'd done a pretty nice job of building and integrating that addition onto the trailer. Those sonotubes, even though they were only 2 feet in the ground, they were all still straight, and that really goes to the quality of the soils there. Very sandy, very well drained, and I think that the frost the material is just good enough for the water to drain away. The site is also kind of on a little mound, basically slopes away from the house site in all directions, which is kind of perfect. So Ford's decision was that he wanted to put in a slab, put radiant heat in the slab, and build on that. And we started in that process, and we're back and forth about how to do the slab. Eventually we calculated out the cost of just making a 12-inch thick slab all the way across versus the cost of making it 12 inches around the perimeter and thinning it down to maybe 6 in the middle. It was about an extra $1,000 of concrete, I think. But when you figure that we would have had to spend $400 or $500, maybe even $600 on stone to fill in and raise up the middle of the slab, it just seemed to make sense to just do the whole thing in one thick chunk of concrete, which Ford put a ton of rebar into too, because he's a welder, and so he welded up a bunch of rebar cages. That slab's never going anywhere. The original motivation or inspiration for the way we built it, I think, came from the garage port, which is the structure we built on the back of our house 4 or 5 years ago. Ford and I did that. We framed that. We tried to do that cheaply and quickly, and we framed it out of logs. And it really looks nice inside. When we built that structure, the sawmill wasn't working, hadn't gotten the sawmill working then. So we just used the logs straight up, round all the way around. Tried to use straight ones for the rafters. And the rafters on that building were 22 feet long. So quite long rafters with a nice long tail overhanging. And they're pretty straight, but you can see that the roof is anything but flat. It works, doesn't leak, and it was cheap and sort of quick. But on this one, on Ford's cabin, because it was going to be a house and because we had gotten the sawmill operating, we decided to flatten one or two sides of each of the logs so we had a frame of reference, and also so we had a flat outside edge to work off of and to measure from. I was very impressed as we did that, running the mill down the one edge of the logs and taking off a little slab, and how little waste there was. previous to cutting up these logs for Ford's cabin, I'd cut up a small load of logs that had been laying around. And I'm not a great sawyer, and we're just learning to use that sawmill, but there's a lot of waste and a lot of slabs and just throw away. When we cut up the logs for Ford's cabin, we just took a thin little slab off of each side, very little waste, which meant that most of the logs we used were essentially cull logs. They were small trees, most of them barely big enough to make a couple 2x4s, maybe a 2x6 out of. And I got to believe there's also some structural advantage to using wood in log form where the rings of the tree are all concentric, the way they grew, rather than, laying in the wood however they are when you cut them into a piece of dimension lumber. The basic concept is to build a log frame, keep the whole structure inside the building with you. So you've got those natural materials, which always feel good, and just the aesthetic of the structure inside the building with you, instead of either concealed in the walls like in a typical stud frame, or sort of partially buried in the walls like it sometimes is in a timber frame. For the joinery on this, even though we used a lot of hand tools and it kind of looks old-fashioned, it's really not. It's mortise and tenon joinery, but heavily modified. The concept here, again, is to do what works best. So we used mortise and tenon, which works really nicely for compression and really well for support, but generally in a typical mortise and tenon structure, terrible on tension. Any tension member is only held by the peg, and the peg just has to blow out the little bit of end grain between it and the end of the tenon, and then it's not really holding anything. So what we did were these short, stubby tenons, plenty to carry the load down, and then we secured them in place with timber locks or GRK screws. And on the critical ones, we also drove those big 3/4 inch pieces of rebar in. So there's no way for the tenon to come apart unless the screws fail or that slides off the rebar, which is pretty unlikely. And then on the outside, Ford doubled up some of them with some truss plates he'd bought. So really kind of a new old joinery, using mortise and tenon where it makes sense, and securing it, strengthening it with modern fasteners. In the design of the building, there's also structure. For instance, the floor plates that carry the beams that carry the upstairs floor, those are let in from the outside of the post. You can see them here. And so they can't separate because of the truss plates and the screws and whatever, but they also can't separate because the floor joists, which are attached, to the top of these beams, those are all holding them in place. And so there's no way for them to come apart or come out without breaking the grip of the floor joist above them. And the same way, the outside floor joist is let in from the outside of the post, and the floorboards tie all those floor joists together. So in order for those floor joints to come apart, they would have to separate themselves somehow from the cross tying of the floorboards. It's also true on the rafter plates upstairs. We had the building's 20 feet wide along the gable end, and then we put a 2-foot overhang on each end, so 24-foot ridge plate. So we did that in two 12-foot sections. So there's a joint in the middle. Obviously, anywhere there's a joint, that's a weak spot. But in order for that plate to ever separate, the rafters, which are screwed into each plate and are sheathed together, they would have to somehow separate. So there's not really any way for that joint to come apart either. There's some other peculiarities about this design, partly because we're figuring it out as we go along. You see that we put vapor barriers on the post bottoms so that the posts can't wick up any water from the concrete. I don't know how much of an issue this really is, because the concrete under the slab is a Stego radon barrier, moisture barrier, thick, I can't remember how many mils, but thick piece of plastic. So maybe that's not even a problem. There aren't any plates Ford didn't want to have any pressure treated wood internal in the house. So there are no plates on top of the concrete. And this did give us some struggles. Mostly Ford had built some or welded up some little chairs that we were going to set into the concrete and use these to secure the posts to the concrete. And we just delayed too long, and the concrete got too hard, and we couldn't put those in. So instead, he made some just flat. So instead, he made some flat stock with some holes in it. And we drilled those into the concrete below the level of the PEX radiant tubing, and then screwed the posts into that, which actually worked really well. But there's still no plate on the slab, so securing to the slab is difficult. And I should go back and mention that having that thick 12-inch slab it's also important that the slab is thick like that, because all the load from this building comes down in the 9 points where the posts rest on the slab. There's no distributing the load all along the wall of the slab on a plate. It all comes down on the 9 points of the post. So the rebar and the thick slab's probably a good idea in that for that reason. One thing that I've been working on in this building is the perfect walls concept, which, as near as I understand it, and if I can simply explain it, is to have the building completely encased in insulation instead of putting the insulation between the structural members like you would in a typical stud frame building where you've got insulation between the studs. So you want a complete wrap of the building with insulation, no thermal bridging by the structural members, and you want a airtight building, and you want behind the siding, you want some sort of gap so that any moisture, that any rain that manages to get driven through the siding isn't trapped between the siding and the sheathing, but has a plane that it can evaporate out of. And similarly on the roof, we made a gap on the roof so that any moisture that manages to get driven through the roof, or even condensation on the roof, has a means to escape. But this perfect walls concept, a complete wrap of insulation with no thermal bridging, and a rain screen so that the water can't get in and start rotting the building there. It's really a fairly simple concept, but it's kind of difficult to sometimes figure out how to integrate it into the building. For instance, we sheathe the roof, and then we put a layer of foam on the roof, but that foam has to make a connection with the foam that comes up the walls, and that's why we cut these gaps through the sheathing so that we could bring that foam up in one integral wrap around the building with no gaps. I think there are two reasons for this. Obviously, the first is the problem of thermal bridging, where if you look at often you look at a roof on a frosty morning and you can see frost on the roof, but not in the places where the rafters are, because the heat from the house has come across those rafters and melted the frost right in those places where the rafters are. That shouldn't be a problem in this building. Got that thick layer of foam, and then we sheathed on top of it, and then we put the grid of strapping on top of that so that there's room for air movement right under the roofing material to dry out any moisture that makes it in there. But it did make this problem where we had to cut this gap in the sheathing so we could bring the insulation package around the wall, from the roof around the wall, without any breaks. The only place we violated this concept is on the rafter tails and the plates, the rafter plates, where they protrude from the building. And the reason for doing this is just because it looks nice. And we figured we can seal those areas with spray foam. But that's the other reason, I think, for the perfect walls concept. Anywhere you have your structural members protruding through the insulation layer, then that's an obvious location for shrinkage or cracking of the foam, or some sort of failure that causes a gap that air can travel through. And once you have air traveling through there, then you've got moisture in the air from the house. And when that moisture hits the cold air outside, certain times in the year, you're going to have condensation, and then you're going to get rot. we were confused a little bit about vapor barriers, vapor retarders, which, as far as I can tell from hours of watching YouTube videos, is a subject that still confuses a lot of people. The rigid foam we're using is a vapor barrier. So theoretically, if the foam is continuous and well sealed, and we're using 2 layers of foam so that the joints will all be taped but also overlapped, there shouldn't be a vapor barrier needed. The foam itself will be the vapor barrier. However, we did want to put some Typar on the roof, and no, Typar is not meant to be used in a horizontal application like that. But here's the reason. Ford got some wood, rough cut pine, got a good price on a bunch of it, pretty dry, but it wasn't shiplapped and it was just rough, all 4 edges. We used that to sheathe the roof. Ford ran one edge through a little planer, cleaned it up, and it looked nice. And we jacked it together to try to get the gaps as tight as we could, but it's inevitably going to shrink up a bit and gap. And when it does, you're going to be looking through those gaps at the foam. And so we wanted some dark membrane in there so it looks at least just like a dark crack, not like a pink piece of rigid foam. And we thought about different things. Tar paper was the obvious thing. Ford thought didn't necessarily want that inside the house, in the house environment. We thought about just taping them with masking tape. But in the end, we used the Typar, which is quite permeable, but is an air barrier. So the hope is that even if we end up with a leak of air potentially around some of the rafter tails or something, we will have been able to fold this Typar into that location neatly enough to stop that air from traveling through there. We'll see. It's a bit of an experiment. We also did not put any sheetrock between the foam and the wood. I have mixed feelings about that. We were rushing to get the roof on. It's an additional expense, but it is a fire barrier, and foam is toxic when it burns. So in the event of a house fire, just got to get out. The wood, 1 inch of wood, is also, I think, a 30-minute fire barrier or something like that. But that's a design thing I think I would revisit in the future and maybe do differently.